Thank you for all of everybody who stuck around for this last part. This will be the most entertaining part of today. My name is Ryan Richards. I'm an inorganic chemist, and metaphorically what I've come up with for you today is I'm trying to teach old dogs new tricks. And by this, I'm an inorganic chemist. The metaphorical dogs are the elements of the periodic table, and I am the Cesar Millan trying to teach these elements how to do new things. And we do this through inorganic chemistry, and we do this for a number of applications, particularly focused around renewable energy and sustainability. There's been a lot of talk today about carbon capture and that as a global grand challenge. There's been a little bit of discussion about just how immense the scale on which this needs to take place is going to be and how we're going to go about doing this. So there's a number of different paradigms out there for how teams have approached capturing CO2 and from different streams. So there's capturing CO2 from smokestacks, and then there's direct air capture from directly from the atmosphere. The most common paradigm is to increase the surface area of some material. So if we just take something, all three of these cubes have the same mass, the same amount of some solid material, but as we cut it into smaller and smaller pieces, we can up the surface area available for doing work for us, such as capturing CO2. If we go to 1 nanometer cubes, we go up by a factor of 10 million in terms of our capacity for capturing CO2. This is my periodic table of natural abundance. The things in the big green circles are things that we have a lot of. The things that are in the small circles are things we don't have very much of. And paradoxically, most of the things that are really good for renewable energy technologies are unfortunately these things at the bottom of the D block. Now, I know all of you have been dying to forget your inorganic chemistry from the past, but the D block here is along the bottom, right above the red X's. That's where your platinum, osmium, all of those wonderful elements are found. So when I talk about the old dogs, these are very old dogs. These elements have been around for a very long time, and we need to find ways to teach these big circles how to do new stuff, how to impart new capabilities to these old dogs. So our toolbox here for doing that as a chemist are we can alter the composition of a material. So you take a sodium, you take a chlorine, you put it together, you form sodium chloride, and you can put it on your steak, and it makes it delicious. We can nanostructure, so we can make things with higher and higher surface areas, and there's some other effects that come into play there. And the third tool in our toolbox, which has just emerged, say, over the last 15, 20 years, is shape control. And so this is for solid materials. They form together by these unit cells. And so this is as technical as this is going to get, but a unit cell is the smallest building block that solids are formed from. And if we take those building blocks and we cut them along, say, the X or the XY vector, you get different orientations of the atoms at the surface. So what I really need you to take away from this are these gray structures at the bottom. Depending on how we cut that unit cell, you're going to get different orientations of the atoms at the surface, and they'll do different tricks depending on how you do that, okay? So here, for example, we have magnesium oxide, and for many years, theoreticians, theoretical physicists, theoretical chemists, depends which building you're in, will do calculations and tell you what different structures will do. And in, say, between 2000 and 2005, there were a number of studies that said, if you can make magnesium oxide or other structures that form this crystal structure, so this is the simple rock salt structure where you have these alternating say, white and purple across the surface. Looks like a checkers board. But if you take this and rotate it, and you cut that, you can form a surface which is all purple or all white. And that is what we decided to look at. So this business of looking at different facets in their activity, for about a decade, this has been something driving the catalysis enterprise. So you get different activities and selectivities depending on which orientation of, say, platinum you get. For metal oxides, we decided to look, and this was the first ever study, looking at surface orientation or faceting for CO2 for adsorption technologies. And JACS, so the Journal of the American Chemical Society, is the best chemistry journal. And we looked at this, and of course, just your regular off-the-street magnesium oxide doesn't really do anything. So we're looking at, on the y-axis, the amount of CO2 taken up, on the x-axis, the partial pressure. So what you would really like to see is something take up a bunch at really low pressures. That means that it could absorb CO2 at, say, atmospheric pressure. If we do the nano system, we get a little bit better. It can take up some. But then if we take the magnesium oxide with this 1-1-1 orientation, this really does pretty darn well, and especially you'll see right there at the beginning on the far left of that x-axis, it's already absorbing quite a bit at atmospheric pressure. And so this is really encouraging. And then Sarah Schilde, the graduate student here, went out and did something that I would have completely advised her against, which was to heat this stuff up. So remember that every paradigm, every report out there for increasing the uptake of CO2 revolves around increasing the surface area. If you take a solid material and you heat it way up, they sinter and it loses surface area. This stuff, she heated it up, she lost surface area, but the CO2 capacity went up by 65% as a result of doing that. And there were some surface reorganizations there. So this is really exciting because we have stuff which is, magnesium oxide is the second most abundant compound in the Earth's crust. It is literally as cheap as dirt. And now, through alternating temperatures and partial pressures and the amounts of hydration present, we can get CO2 uptake. So there's a lot of, this is exciting. This opens up a whole discussion with a whole number of questions that we need to answer. So we need to hire a whole bunch of graduate students and have them come and look. But is there a selectivity issue? So there's other things in our atmosphere other than CO2. So are they competing with each other? Is it possible? What are the limits on how much we can take up? What about mixed oxides? What about other dirt? Can we mix dirt together in different ways and get it to surface restructure and do some stuff for us? Ultimately, it looks like we're going to, a major part of carbon capture is at some point you got to release it to do whatever you're going to do, if you're going to geologically store it or convert it to something. So you want to have some mechanism by which it doesn't cost you very much energy to release that CO2 that's been captured. And finally, is it recyclable and scalable? So with that, I will leave you. I have to go teach a class at 4. I'll be at the reception at 5. Thank you very much for your attention.